In the name of Almighty God, I'm Master Hassan Koshi, and today I want to talk about transfer rate estimates between deuterium to palladium nuclei. Section 5.3 provided the first estimate for excitation transfer rates from deuterium donor systems to helium-4 receiver systems. It was found that under realistic experimental conditions, expected transfer rates would be unobservably low. Another key insight from that section was that relativistic coupling is significantly stronger and therefore more relevant for the processes under the consideration here than magnetic dipole coupling and electric dipole coupling. In sections 5.4, palladium nuclei were introduced as receiver systems and different kinds of palladium excited states discussed. We expect indirect coupling between the two transitions deuterium helium-4 and palladium star per palladium to work similarly to the resonant excitation transfer model of sections 5.2 because of the comparatively high standard of realistic couplings as seen in the 5.3. We focus on the ACP interaction for both transitions. We know that the magnetic quadrupole M2 of the ACP interaction can provide for direct coupling between the deuterium P3 J is equal to 1 and 2 states and the helium-4 states, so that the use of a direct matrix element is appropriate. We don't expect there to be a significant direct coupling between the ground states of palladium isotope and excited states, bound states, or a cluster base nuclear molecular states, for example, Ru and plus helium-6 state, the direct matrices element would be hindered. Depending on what fractional admixture, a superposition of such clusters were already present as a part of the palladium isotope ground state. Before getting to the actual rate estimates, we start with a discussion of notation as small variations in notation will become useful in later considerations. Recalling the expression for the excitation transfer rate, the derivation of decay factors in 6.12 yields expressions for the minimum and maximum rate of excitation transfer. Following equation 6.69, the minimum rate is gamma minimum is equal to absolute omega RB square root n deuterium n r palladium, where omega RB refers to the generalized Rabi frequency for oscillating between the transitions in group A and B. The generalized Rabi frequency is equations 57. We have 1 divided by 2h at root omega RB is equal to V agent to the power of 2 divided by delta E is equal to V agent to the power of 2 divided by delta MC to the power of 2, where again we add a subscript V agent as previously down in equation 75 to differentiate referral to a generic interaction from a concrete one. The minimum rate at which the corresponding decay factor is therefore gamma minimum is equal to 2 divided by h v agent to the power of 2 divided by delta m c to the power of 2 square root n deuterium n r palladium. In the case of transfer from the deuterium donors to the helium-4 receivers, the transitions involved on the another donor and receiver sides are the same, and so for v agent to the power of 2 we had a u to the power of 2. For the case of the transfer from deuterium donor to the palladium receivers, the variable u is equal to u0 e to the power of minus g denotes the coupling for the fusion transitions, and v is equal to v0 omicron palladium denotes the coupling for the palladium transitions per the diagrams in the figures 23 and 24, and for v agent to the power of 2 we get uv. Figure 23 illustrates resonant nuclear excitation transfer of 23.85 megaelectronvolt from the deuterium to the helium-4 fusion decay to the palladium R tends to palladium I star excitation, where the latter states is an exemplary case of palladium star A. Note that in actually this kind of star excitation transfer process involves pathways through different possible intermediate states, which exhibits an asymmetry in how they are affected by loss represented by eta in figure 24. You see there is a plot here. It's based on the energy helium 4 based on the mega electron volt. In the left sections we have a system A, in the right sections we have a system B. In system A we have a Colombo barrier, and this Colombo barrier from the helium 4 to the deuterium, you see we have a nuclear tunneling. When we want to have a deuterium tends to a helium 4. Here in Colombo barrier it is indirect coupling, and you see H omega 0 transfer rate is gamma U0 V0 omicron palladium e to the power of minus G, and you see the magnification of these two um, deuterium here. Figure 24 illustrates resonant nuclear excitation transfer between deuterium and helium-4 decay transition and a hypothetical resonance palladium star per palladium excitation transitions by indirect coupling via a shared oscillator mode destructive interference between the upper and lower intermediate. For example, virtual state is reduced by selective loss in the lower pathway, allowing for resonant nuclear excitation transfer to occur here, represented by eta per section 6.5 and 6.6. There is a here in the left side a palladium or deuterium to the H omega 0. We have two directions, one for intermediate states visual for positive n plus negative m, and also the negative n plus minus m, which will be converged to the negative positive n, and you see that we have helium 4 or palladium R star and H omega 0. Note that equations 137 refers to the ideal loss case in sections 5.2. To account for realistic loss, the correction factor absolute 1 minus eta needs to be applied, resulting in gamma mean is equal to 2 divided by h absolute 1 minus eta uv divided by delta m c to the power of 2 square root n deuterium and a palladium I. In sections 5.3, we found that among the three couplings considered, magnetic coupling, electric coupling, and relativistic coupling is the strongest, which is why we proceed focusing on relativistic coupling. For relativistic coupling for the deuterium helium 4 transitions, recall from the equation 5.3. U is equal to absolute deuterium I z helium 4 C square root palladium helium 4 to the power of 2. Equivalently, for the palladium stars per palladium transitions, we have a V is equal to absolute palladium star absolute AZ absolute R multiplied by C square root P palladium to the power of 2. Useful variations in notation. We can simplify the notation by pulling in the decay factors with the variables for the coupling strengths according to here, exemplary for the minimum rate scale. U is equal to U multiplied by square root n deuterium nu is equal to V multiplied by square root n R palladium, resulting in gamma transfer is equal to 2 divided by H as with 1 minus eta UV divided by delta MSc to the power of 2. We can further simplify this notation by pulling the correction factor with u, resulting in delta u is equal to absolute 1 minus eta multiplied by u. Delta u is equal to absolute 1 minus eta multiplied by u. The notion of delta u refers to the original of that terms as difference between the two pathways in the diagram in figure 24, where one pathway is affected by loss and the other is not. Finally, it will be useful to have normalized the coupling strength of a transition, such as the nu by transition energy delta E multiplied by delta M C to the power of 2. This then results in dimensionless coupling parameter G. G is equal to absolute nu divided by delta M C to the power of 2. The result is further simplification of the expression of the excitation transfer rate, equation 137. It can be alternatively written as if gamma transfer is equal to 2 divided by h absolute delta UG. We expect perturbation theory to give good results for the weak coupling limit where G is less than 1. For the strong coupling limit G is greater or equal to 1. We will need to implement a non-perturbative analysis to get reliable results. We will consider transition from weak coupling to strong coupling in sections 5.6. We will make use of this alternative notation later in the text since it will be simplify a number of important considerations. For now, we will return to the notation of equation 143 and proceed based on the gamma transfer is equal to 2 divided by h absolute 1 minus eta u divided by delta msc to the power of 2 with the starting place being the version with the minimum defect factors. Gamma minimum is equal to 2 divided by h absolute 1 minus eta UAV divided by delta MSc to the power of the square root n deuterium n palladium R. First rate estimate for excitation transfer from deuterium to palladium. The key difference to the rate estimate of sections 5.3 is the interaction term, which is now UV instead of U to the power of 2 due to the palladium star palladium transition. Coupling V being different from the deuterium helium 4 transitions coupling U. This gives an overall coupling strength for excitation transfer between deuterium and helium-4 transitions and the palladium perpalladium transitions. All UV relativistics is equal to phi deuterium absolute R phi helium-4 multiplied by 6 to the power of 2 phi helium-4 phi palladium R multiplied by phi palladium star R absolute R multiplied by IZ phi I palladium, where per section 6.15 absolute phi deuterium absolute IZ phi helium 4 is equal to zeta helium 4 or zeta j is equal to 1 and j is equal to 0, which will be concluded to near 0.0362 square root nu nuclear divided by nu molar e to the power of minus g. And per section 6.16 we have a phi palladium star absolute r multiplied by iz phi I palladium is equal to 2.6 multiplied by 10 to the power minus 5 omicron. So the idea here is that for a fully allowed single nuclear transitions at 23.85 megaelectron-volt, we would accept the magnitude of the A matrix element to be roughly 2.6 multiplied by 10 to the power minus 5. The Omicron factor can be thought of as the square root of the normalized M2 transition strength for the transition. Since our knowledge of how big these transition matrix elements are in the palladium isotopes is limited, we will express matrix elements and rates in terms of Omicron values, keeping in mind that if the transition is weak, that we would expect Omicron is less than 1. The above expression results in these equations. UV relativistics is equal to 0.0362 square root nu nuclear divided by nu molar e to the power of minus g and square root ma helium 4 ma palladium R C to the power of 2 divided by N. P dissipation tau multiplied by 2.6 multiplied by 10 to the power of minus 5 omicron. Consequently, based on equation 149, the minimum transfer rate is gamma minimum is equal to 2 multiplied by absolute 1 minus eta multiplied by 0.0362 multiplied by square root mu nuclear divided by nu molar e to the power minus g multiplied by 2.6 multiplied by 10 to the power of minus 5 omicron multiplied by square root m helium 4 ma palladium star C to the power of 2 divided by delta m is c to the power of 2p dissipation tau divided by h multiplied by square root n deuterium n palladium divided by n. To evaluate this expression, we need to consider the values of all relevant parameters. We take absolute 1 minus HI is equal to 0.1, and nu nuclear divided by nu molar is equal to 6.65 multiplied by 10 to the power of minus 12. G is equal to 90.35, where absolute 1 minus eta is for the deuterium 3 plus 1 helium 4 contribution to the deuterium helium 4 transition per section 6.5, and where the volume ratio and the gamma factor G take on the values determined in section 3.6. For the Omicron value, we consider the following realistic choice for the purpose of these sections. Although we will provide a more detailed discussion of this parameter later in sections 5.8. Omicron is equal to 0.001. Moreover, n deuterium divided by n is equal to 0.25 multiplied by 1 divided by 9, and then palladium R divided by n is equal to 0.25, where we assume a highly loaded lattice with mono vacancies where 20% of the deuterium molecules are in the P3 state. See figure 23.8 in section 6.1, with only one of the 9 possible P3 states, with J is equal to 1, being involved in the RCP transition sections 6.9 and 6.8, and where the natural abundance of the average palladium isotope involved in the palladium isopalladium transition is 0.25. Since we don't yet know exactly which palladium isotopes exhibit best suited levels, note that these values for the number of donor site and receiver site systems per unit cell differ from those used in the sections 5.3. Since we now consider palladium nuclei as receiver systems instead of helium-4 nuclei, the Na palladium divided by N ratio is comparably high, and the assumption and underlies the derivation of decay factors in sections 5.2, namely that the number of receiver systems exceeds the number of donor systems is met. On the donor side, the choice of the N deuterium divided by L is motivated in section 6.21. For the more characteristics, we choose experimentally plausible values for the vibrational power dissipation and frequency applied to the lattice as P dissipation is equal to 1 watt, FR is equal to 5 megahertz, resulting in a tau for acoustic phonos of tau is equal to 10 to the power of minus 12 multiplied by 10 to the power of minus 7, FR divided by 1 megahertz to the power of minus 3 divided by 2 seconds is equal to 0.003 seconds. Plugging in all of the above values results in a minimum transfer rate on screen of the tau minimum on screen is equal to 4.79 multiplied by 10 to the power of minus 22 1 per second. Since we use the on-screen gamma factor G above, we can consider the effects of scaling by multiplying with per section 6.3 e to the power of delta G screen, where for 350 electron volt screening potential, section 6.3 delta G screen is equal to 49.2. This results in tau minimum scale is equal to 1.21 per second. To obtain the maximum peak rate of the decay enhancement pulse, we apply the additional decay enhancement as derived in sections 5.2. Tau maximum is equal to tau minimum 1 divided by 4, and reduction for any reduction is equal to 10 to the power of 15. This yields tau maximum screen is equal to 2.79 multiplied by 10 to the power of 14, 1 per second. Again, this is population level transfer rate. For example, the rate at which the ensembling group A transfer excitation to the ensembling group B to obtain a rate per deuterium pair that is comparable to the estimate given by Konin and Noemberg 1989 in reference 20. We normalize the expression taking the decay enhanced expression we obtain tau maximum screen divided by n deuterium is equal to 0.28 1 per second, such as a rate estimate means that this kind of the excitation transfer would get into the observable range. Let us therefore also consider the minimum rate per deuterium to get a better sense of whether the process of time evolving decay factors from the minimum of the to the maximum rate has a chance to get started. Time minimum and screen divided by energy temperature is equal to 1.12 multiplied by 10 to the power minus 15 1 per second. Discussion sections. We need to find that in the given scenario, minimum and maximum rates are in the observable range. Note, however, that we worked with an idealized model which didn't include dephasing and which made assumptions about the existence of single resonant receiver states. A model that includes reasonable estimates for dephasing would show no observable current effects due to this mechanism. In later sections, we will consider more realistic models. Note that for the sake of simplicity in this section, we assume comparatively low steady-state dissipated power of 1 watt. However, under realistic conditions, power can be expected to fluctuate. This means that instead of having a fixed value of P dissipation, we can expect P dissipation based on the time, which is a variable based on the time. We refer to power maximal as high power transient. In the following sections, we will consider the effect of high power transient on the transfer rate estimates and startup dynamics. Note also that this time evolution of decay factors has to take place between the constraint of the decoherence time of the system. We provided an estimate for the decoherence time in section 6.21, yielding a value of about 1 nanoseconds. Moreover, in the estimate above, we assume a value of the Omicron factor of 0.0016. Many transitions in palladium isotopes and other mid-sized nuclei have not been identified and characterized. The existence of transitions with a wide range of different Omicron values is conceivable, impacting rate estimates and startup dynamics. Therefore, in addition to high power transients, both the decoherence time and the Omicron values are important constraints. Section 5.8 is dedicated to a discussion of such constraints. Finally, we assume in the sections of existence of a hypothetical palladium state at 23.85 megaelectron volts that meets the resonance conditions for the deuterium helium 4 transitions. However, as pointed out earlier, the existence of a single stable life that is highly unlikely. Section 5.7 contains a conjecture how the resonance conditions can be met alternatively given multi-stage transitions to a combination of realistic palladium states. Now I want to go through the sections and chapter 5.6, the effect of hyper transients in the lattice modes and on excitation transfer rates. In the previous sections, we obtained a first preliminary rate estimate for excitation transfer from deuterium to palladium. The resulting minimum rate for the ensemble was large comparable to the rate of the spontaneous fusion, but still small given a short decoherence time of about 1 nanosecond. The estimated maximum rate is significantly higher, but with a minimum rate that is too slow. A system doesn't have enough time to evolve to the maximum rate. At the same time, the assumptions of 1 watt of dissipated power in a Phonon mode across the coherence domain with cycles of about 3 milliseconds is conservative. In these sections, we consider the effect of the occasional transients, where for a short time there is a high power peak in vibrational power. However, to anticipate the results of these sections, we will find that in the present picture, the high power transient requirements for the observable fusion rates are unphysically extreme. Studying the effect of high power transients suggests evolution of the rate expressions time minimum scale of equations 154 as a function of P dissipations. Another variable of considerable uncertainty is the nuclear transitions factor omicron, which is a characteristic of the palladium transitions involved. To gain intuition about the dependence of the transfer rate on those two variables. The goal of this section is the creation of the counterplots that illuminates these relationships, testing for a strong coupling. Before evaluating the transfer rate across a large parameters space of P and O values, we need to remind ourselves that the previous calculations were based on the perturbation theory, which assumes that the coupling strength driving a transition is small compared to the transition's energy. This relationship can be expressed through a dimensionless coupling constant G. If G is close to unity or larger, then a perturbation theory approach needs to be replaced by a strong coupling approach. Since there are two transitions involved in the transfer from deuterium to palladium, we have to evaluate a dimensional coupling constant for each. However, because the coupling strength for the fusion transitions is hindered by the Coulomb barrier as represented by the e to the power of minus g factor, the g associated with the fusion transition can be readily identified as less than the one. For the dimensionless coupling constant on the deuterium side, we have G deuterium pair helium-4 is equal to U divided by delta E. For the dimensionless coupling constant on the palladium side, we have this equation. For simplicity, we take G is equal to G palladium star divided by palladium, and following equation 147 tau transfer is equal to 2 divided by H absolute delta U G. We are now ready to plot G evaluating equation 170 yields. Recall the derivation of the Poisson matrix elements in equation 6.16. The result is shown in figure 25. Figure 25 illustrates palladium dimensionless coupling constant G for the palladium nuclei as a function of the transit dissipated acoustic phonon energy. For example, the product of the dissipated transit power and pulse period in the associated acoustic mode and the palladium omicron value. The transition from a perturbative to a strongly coupled system is defined by the G is equal to 1 red line and the exemplary case of the 0.003 joule of dissipated energy from the acoustic phonon mode dashed white line and its intersections with a palladium star palladium transition with an omicron value of 0.001 with X mark are shown. Transfer rates with a crude extrapolation for the strong coupling regime where G is larger than unity. The relationship between G and transfer rates tau transfer can no longer be considered linear. In the strong coupling limit, the situation is more complicated as will be discussed in the next sections based on the what we know so far, the predicted excitation transfer rates are slower than our estimates for the difference and loose rates. What we will do here is a crude extrapolation based on FG is almost equal to J divided by 1 plus 2G. 2G. Figure 26 illustrates plot of the minimum nuclear excitation transfer rate with the 350 electron volt of electron screening. Tau minimum screen from the deuterium deuterium helium 4 decay transitions to palladium star palladium excitation transition as a function of the transient dissipated acoustic phonon energy. For example, the product of the dissipated transient power and pulse period in the acoustic mode in the palladium omicron value, the exemplary case of 0.003 joule of dissipated energy from the acoustic phonon mode dashed white line and its intersections with palladium star transition with an omicron value of 0.001 white X mark are shown here. Thank you so much for watching my tutorial video until the end. Today is the 8th day of the July 2026 and time is near the morning. If you want to download any simulation which is near or similar to this literature, you can find it from github.com/masterscript/kashi script or github.com/safroi script.